So here we're going to take a look at alkyne alkylation reactions. The alkyne alkylation reactions are a reaction that are specific to terminal alkynes. So terminal alkynes, you should recall, are alkynes where one side of the alkyne has a hydrogen on it. And the reason that this reaction is specific to terminal alkynes is that you need this hydrogen on the alkyne in order for the reaction to proceed. So this reaction takes place in two steps. The first step is the addition of a strong base such as sodium amide. And then in the second step, an electrophile, usually an alkyl halide, something like methyl iodide, is added. And as a result, whatever that alkyl group is will end up on the alkyne in place of the hydrogen. So how does this reaction work? And why does this reaction work? So mechanistically, the reaction is at least initially fairly straightforward. The strong base NH2- is able to remove the hydrogen on the alkyne and form the anion on that carbon. In a second step, the anion will attack the electrophilic carbon and force the carbon halogen or the carbon leaving group bond to break. That gives us our product. So a couple things to sort of think about or remember with this reaction. The first is, while there's two steps in this mechanism, as we're going to see, these two steps are pretty routine steps. The first step in this reaction is just an acid-base reaction. We're using a strong base and we're removing a hydrogen. The second step, and this terminology may or may not be familiar to you at this point, but this second step we call an SN2 reaction. And if you haven't taken Organic 2 yet, then that name is probably not familiar to you yet. But when you get to Organic 2, this is actually the very first reaction that we're going to cover. So why is this reaction able to work as well as it does? In general, we know that alkanes and alkenes, if we added this same base to it, NaNH2, which is still a relatively strong base, most likely nothing will happen. Yet, when we add that same strong base, sodium amide, to a terminal alkyne, we're able to form an anion. Well, the primary difference here is the hybridization. Alkanes, sp3, sp2 for the alkenes, and of course sp for the alkyne. With an sp carbon, we know that the electrons in an sp orbital are more tightly held to the nucleus than those in sp2 or in sp3. That helps to stabilize those extra electrons. And so what it means is that an anion formed from an alkyne is more stable than one formed from an alkene or an alkane. given that this conjugate base is more stable, that means an alkyne is a stronger acid than an alkene or an alkane. And if we want some numbers to work with, the pKa of an alkyne is approximately 25, whereas the pKa of an alkane is usually somewhere on the order of 55 to 60. So that's our first piece on this reaction. The second piece to look at is the electrophile. And you'll notice in the first example I used, I had a very, very simple electrophile, methyl iodide. And basically, we are very limited with the electrophiles that we can use. So the alkyl halide for this reaction has to be primary and maybe secondary, but never tertiary. So if we tried to do this reaction and we use tert-butyl iodide as our electrophile, this reaction won't work at all. As we'll learn more with SN2 reactions, having all of those carbons on there makes it too sterically hindered, and so when this tries to do its nucleophilic attack, it doesn't have enough room to fit in there. The second thing we have to be careful of is whether there are any adjacent hydrogens to the leaving group. So here we have 1-iodopropane as our electrophile. But 1-iodopropane has 2 hydrogens that are on the carbon adjacent to the leaving group. And so that means, as we'll learn later on, that there is a second reaction known as elimination that will compete. And in many cases, the elimination will dominate. So if we want to make sure that the reaction we're looking at for an alkylation is going to work, we want to make the leaving group as unhindered as possible, primary or secondary at the most. And second, we don't want any adjacent hydrogens. So let's take a look at a couple of examples now. So an alkyl halide like the one we have here is a good example of one that can work well for this reaction. The leaving group here is primary, and the adjacent carbon, which is this one, has no hydrogens. One like this would also work well because, again, it's primary, and in this case the adjacent hydrogen, while it's there, it's on an sp2 carbon, and it turns out that those are not as easily removed. So finally, what are the limitations of this reaction? Well, we've already seen there's some pretty significant limitations with the electrophile, but what about the alkyne? what functional groups do we need to avoid? Well, basically, we need to avoid any functional groups that either have acidic hydrogens or have leaving groups themselves. So pretty much any carbonyl is problematic. Carbonyls are good electrophiles, and so those can prevent this reaction from working. Alcohols can be problematic. But the primary one that we want to avoid with an alkyne alkylation are carbonyls. Carbonyls have the ability to cause problems both because they're good electrophiles, as well as carbonyls can have acidic hydrogens in them. But otherwise, the alkyne alkylation is one of our first reactions that actually allows us to form new carbon-carbon bonds. And as we're going to learn about later on in synthesis, the formation of carbon-carbon bonds is what allows us to put molecules together.